Our first example that we are going to cover today is on rotational and projectile motion. So there's a ball attached to a rope swinging with a radius of 3 meters. And at point P, the ball is then released and launched at a certain angle and initial velocity. So it travels as a projectile from that moment as it's released from the orbit of the circle. And then it will travel some horizontal distance, and that's what we want to solve for. So we are given that the radius equals 3 meters. The centripetal acceleration equals 6.2 meters per second squared. And the angle at which it's fired is 27 degrees. We also know gravity, and you're given that the height it is at when it is fired is 5.2 meters. Okay, so that is the setup of the problem. And I will switch over to the whiteboard so that we can start solving that. Okay, so let's start by looking at what we're given in this problem. So we have an object is released from a circular orbit. With a radius r. R is equal to 3 meters. And centripetal acceleration is equal to 6.2 meters per second squared. So those were both given. We also know that the height at which it's released is equal to 5.2 meters. And that the angle is equal to 27 degrees. Okay, so given this information, Bhavdeep, where do you think we would start with this problem?
We already given the centripetal acceleration, so I believe we could use that formula to find out the velocity with which it's released.
Okay, I think that I'm having some issues with my audio. I didn't hear that, but were you guys able to hear his explanation? If anybody was able to hear that, please respond to it in the chat. Okay, cool, so it's mine. Let me just fix that. Cool. Okay, sorry, so Bhavdeep, were you saying that we could solve for the velocity in this equation?
That is precisely what I said, yeah.
Okay, great. So we know that centripetal acceleration is equal to v squared over r. Sorry, v squared over r. And because of that, if we know r, we know AC, we can then solve for v, which would be our velocity at the point that the projectile is thrown into projectile motion. So v would be equal to the square root of AC times r. So that would be square root of 6.2 times 3. Okay. So if you solve for that, you are given a velocity of 4.313 meters per second. And that would be your velocity at the initial point of the projectile. So now that we know that, we also know the height and we know theta, are we able to solve for how far it would go in the x direction? Given the fact that we're talking about velocity and distance and angles and all of these factors that we've seen before, it's safe to assume that we're going to need to use our kinematic equations. So our 3 kinematic equations that we tend to use most often would be delta x is equal to v initial t plus 1/2 at squared. V squared is equal to v initial squared plus 2a delta x. And v is equal to v initial plus at. So these are the three that come up the most. And using these three equations, we should be able to solve for our horizontal velocity. So Bhavdeep, which equation do you think we would want to use?
Now, I believe the first equation would be ideal, Drew.
Okay, so if we're using this equation here, the first one, we do have v initial, and we do know acceleration, right? Because we know that there's gravity. And in this case, what would delta x be? Would it be the horizontal distance we're solving for, or
Something else?
something else, right? So if we're looking at this problem in the scope of the y direction, so we're talking about a being gravity, then delta x in this case would be the change in height, which we also have. We have the initial. This would allow us to solve for time. Now, if the problem is asking for delta x, why would we want time?
Because we want to put that in, so say another equation to find out the delta x.
Exactly. We can't solve for delta x directly with the variables we have currently, but if we solve for time and we know how long it's in the air, we can figure out how far it traveled horizontally. So that's what we're going to do. We'll start by solving for time. Okay. So I will clear the whiteboard so that we have a little more space to work. And we've chosen the equation that, delta x is equal to v initial t plus 1/2 at squared. And we know that v initial is equal to 4.313 meters per second at 27-degree angle. Okay, so solving for this, we plug in our delta x is our height, which we know h is equal to 5.2 meters. So seeing as we're calling down negative and up positive in a standard coordinate plane, we're going to say that the change is negative as it is dropping. So negative 5.2 meters is equal to v initial, which would be 4.313 meters per second. But can I say that it's 4.313 meters per second, or do I need to change that into its components?
Well, I believe that since we're just calculating the y velocity, we should calculate the y component and then use that as the initial.
So yeah, because we are talking about x and y distances separately, as a result of that, we will have to break it into its components. Otherwise, all we would be looking at is the total velocity rather than x and y, and even though we're looking at y distances. So that would be 4.313 sine 27 degrees times t plus 1/2 times our acceleration. And will that be 9.8 meters per second squared, or will it be negative 9.8 meters per second squared?
Well, I'd say that would be negative 9.8 since we're taking downwards as negative.
Yes, exactly. So we have to keep that same, our same coordinates that we're calling down as negative and up as positive. We have to maintain that throughout the whole problem. So that's negative 9.8 meters per second squared times t squared. So,
sorry, could you explain why the y velocity is a sine and not a cosine?
right, yes. So we know that the projectile is launched at an angle of 27 degrees with a velocity of 4.313, which means that we have a y component and we have an x component. So if I use my trig rules, I know that y would be the sine of 27 degrees, whereas x would be the cosine, seeing as sine is opposite over hypotenuse, whereas cosine is adjacent over hypotenuse, and the opposite is the y, therefore I know that it's sine instead of cosine.
Wonderful.
Okay. So this is a good idea to definitely sketch out your components to make sure you get your trig correct when you're doing these equations. Okay, so looking at this equation that we have now, we have t squared and we have t. So this format reminds me of ax squared plus bx plus c, which is equations we've seen in math classes before. And how would we solve that kind of equation, Bhavdeep?
The ideal solving method would be using the quadratic formula, which is negative b plus minus root b squared minus 4ac over 2a.
Exactly, yes. So we would have to use our quadratic formula here. So in this case, if I rearrange the equation to look a little bit more like the ax squared, we get that negative 4.9 t squared plus 1.958 t plus 5.2 is equal to 0. So this is just if you multiply your values and arrange them all to be on the same side of the equation to make it look a little bit more like the format we recognize. This is the equation you would get. So using that and plugging it into our quadratic formula, we get negative 1.958 plus or minus the square root of 1.958 squared minus 4 times a, which is negative 4.9, times c, which is 5.2, all over 2 times a, which is negative 4.9. So this is our quadratic formula, and if you solve for that, you get t, which in this case would be equal to, as there's a plus and a minus sign, it's plus or minus the square root, you will get two answers. Your first answer will be 1.2646 seconds, and the second will be negative 0.8496 seconds. So if I've been given two answers, Bhavdeep, how will I know what my result, what my actual answer is supposed to be?
Well, so you got two answers. One of them is positive and the other is negative. And it's clear that we're solving for time here. A negative time, as it happens, does not exist. So that's why we can disregard that as an answer and take the positive one as our true answer.
Exactly. So because we cannot have a negative time, I know that my answer for how long the projectile spends in the air is equal to about 1.3 seconds. And that is how I will use that value to solve the rest of the problem. So I'm going to clear the whiteboard from here. So given that t in the air is equal to 1.2646 seconds, and my velocity initial was 4.313 meters per second at 27 degrees, can I use this to now solve for my final answer that I'm looking for, which is horizontal distance? Right, so going back to those kinematic equations, I can actually use the same one again. So I have delta x, which is what I'm solving for, is equal to v initial times t. I have both of those variables, plus 1/2 a t squared. So I have all of these variables, or I'm solving for all of these variables except for a. Why will that not be a problem, Bhavdeep?
Well, as we know in projectile motion, when moving along the x-axis and just with the x motion, the velocity is constant.
Exactly, and a constant velocity is equal to 0 acceleration.
Precisely.
So in this case, it is just v initial times t. So that again would be 4.313 meters per second. And again, we're looking at components, but this time the x component. So that's 27 degrees, cosine of 27 degrees instead of sine. Times our time spent in the air, which is 1.2646. And that will give us our delta x, which is equal to 4.86 meters. So that will be the final answer to the question. So we started with a rotational motion problem, and using the information that we got from that, we were able to turn that into a projectile motion problem and solve for the horizontal distance traveled. We have an object with that is hanging from one rope, and the rope is actually attached in 3 different places. So once to the object and twice to the wall or to the ceiling. And we would like to find out the tension in each cord if we know that the weight of the object is equal to W. So the information that we have here is that theta for A is 30 degrees, for B it's 45 degrees, and the weight of the object is W. That is all we know about this problem. So I will, again, move this over to the whiteboard so that we can start working on the problem. Okay. So we have cables hanging down, and we have an object hanging from the bottom cable. This is B, this is A, and this is C. So if I break those into 2 different areas, I know that theta B, which is this angle here, is equal to 45 degrees. And that for A, that is equal to 30 degrees. Okay, so based on the fact that we're trying to find out tension and that we're solving for forces, what do you think a logical first step would be here, Bhavdeep?
Well, I believe that since we need to calculate the tension every single string or every single rope, we don't necessarily need to go chronologically. We can as easily go for, say, C first, and then go for the other 2. So I believe the first order of business should be creating a free body diagram of the object, and that way we could perhaps find the tension C.
Okay, so you're saying to create a free body diagram for the box down here.
Mm-hmm.
Okay, so our box with a weight of W is right here. Now, there's the one force that we know is always going to act on anything that has weight is mg, or in this case W, as that is what we're given. And as we can see, it's making contact at the top with another rope, which means that we know that there is a upwards tension force, and that would be T of C. Are there any other forces that would be acting on this object, Bhavdeep?
I believe these are the only forces, Freya.
Okay, so from this free body diagram, can I reach any conclusions that would help me with my problem?
Well, since it's in equilibrium and and it's mentioned that the thing is suspended, we can assume that there is no motion or acceleration and the object is in equilibrium, which would go with, I believe, one of Newton's laws. Which one do you think that is?
So we know that as it's in equilibrium, the sum of forces, the sum of the forces is equal to 0. So that we know that if we're writing out our forces here, we have TC is upward, so it's positive, and the weight is negative. So that is equal to 0. Therefore, we know that the tension in C has to be equal to the weight of the box, which answers 1/3 of our question, as we are solving for tension in every one of the ropes. Okay, so that is the first tension. Can we solve for any of the other tensions using this free body diagram?
I believe we're good, and we can move on to the next, or another free body diagram.
Exactly, yeah. So from this free body diagram, it only shows the problem from, it only shows TC in the problem. TA and TB are outside of the scope of this free body diagram. So in order to solve for A and B, we would have to do a separate free body diagram. And I believe that the point at which it would make most sense to do the free body diagram would be here, as this includes all of the tensions. So drawing a free body diagram for that, we get that we have T of B, and T of A and T of C. I'm going to include the angles on here to help me with my equations later, except I'm going to include the angles down here to make it a little easier for me. So that's 45 degrees, and this would be 60 degrees. Okay. So from here, would we do the same thing, or would writing our Newton's law equations out make sense in order to solve for our values?
Well, I believe we need to decompose both TA and TB into their components, and then we could proceed from there. But could you explain a little bit of how you go at the 60 degrees and where do the 30 degrees go in
Okay.
Projectile?
So 30 degrees would have been the angle up here. So using my kind of geometry rules, I can say that the sum of these two angles, of the upper angle and this bottom angle, is equal to 90. So if I know that the upper angle is 30, then I know that this bottom angle would be 60. And the same goes for the B side of the equation. It just happens to be that 90 minus 45 is equal to 45.
Absolutely.
So just redraw that for clarity. Okay. So kind of going back to our equations here, we do need to decompose it. So if we're looking at, we have forces in the X direction and we have forces in the Y direction. So looking at the X direction first, it might seem like there are no forces in the X direction because you don't see anything along this line. But what we have are components of our tension forces that go in the X direction. So we have TB of X, which would be equal to TB, it would be this force up here. So that would be equal to sine of 45. And minus, as TA is going in the negative direction, TA sine of 60 degrees. And this will all be equal to 0 because, again, we are in equilibrium, so the sum of forces will equal 0. In the Y direction, it's very similar, but rather than being the X components, we're looking at our Y components. So TA and TB both point upwards, so they will have positive components. So we have TB cosine of 45 this time, plus TA cosine of 60. And do I say minus TC, or is there something else in there that would provide me more information about how to solve this problem?
Well, we found out that the weight was that TC was equal to the weight, which is W. So we can as easily substitute that in the equation.
Exactly. So rather than saying minus TC, I can say minus W, which will be a little more useful to me rather than providing another variable that I don't know. And again, this is equal to 0. So these are our two Newton's law equations that we have for the hanging equilibrium problem. And we are going to use these to solve for TA and TB. I'll move this over to the whiteboard, so to a clear whiteboard so that we have a little bit more space. Okay, so TB sine 45 minus TA sine, TA sine of 60 is equal to 0. That is our equation number 1. And TA cosine 60 plus TB cosine 45 minus W is equal to 0. That is your equation number 2. So I have two unknowns and I have two equations. So given that, I know that I can solve for my unknowns. So what I'm going to do as my first step is that I'm going to take equation 1 and I'm going to rearrange it to solve for one of the variables. So I'm going to rearrange to solve for TB in this case. So TB would be equal to TA sine 60 over sine of 45. So here all I did is rearrange so that I separated TB from the rest of the problem. Now, given the fact that I have redefined TB in terms of TA and in terms of just a number value, I can plug this into equation number 2 so that all I will have in equation number 2 is the variable TA and nothing else. So doing that, TA cosine of 60 plus TA sine of 60 over sine of 45. And then don't forget that TB is multiplied by cosine of 45, so you have to remember to include that. Minus W is equal to 0. So in this case, as I know W and I know what sine of 60 is, cosine 45, these are all values. The only thing that is unknown in this problem is TA, which means that I can rearrange and solve for TA. So looking at this, Bhavdeep, do you think there's a way that I could simplify this problem to make it a little easier to look at rather than having so many sines and cosines?
Well, one of the ways could be we have in the second part of the equation, we have a cosine 45 over sine 45, and that is equivalent to a cotangent of 45. So I believe that would make it a little simpler, a little easier in the eyes.
Yes, so there are kind of two different ways you could look at this. You can either simplify it geometrically and say that, I know what cosine over sine is equal to. Another way is that at a certain point, you can also solve for the values. So for instance, in this problem, I could say that cosine of 60 is 0.5 because it is. So 0.5 TA plus, if I multiply sine of 60 times cosine of 45 and divide by sine of 45, I get a value of 0.612 TA. And I can put W on the other side of the equation as I would like to separate my TA from the rest of the problem. So this is a little easier to look at than the previous problem, but it's the exact same values. And now solving for TA, I get that TA is equal to W over 0.5 plus 0.612. Or in other words, TA is equal to W over 1.11, just about. So that would be our final answer for what TA is equal to. So we found out that TC is equal to W, TA is equal to 1 over 0.11 times W. Are we done, or is there still something we have to do, Bhavdeep?
Well, we found TA and TC, but TB is still remaining. So I think we should use the equation that we found from rearranging the first one, and then put the value of TA inside that.
Exactly. So we have this equation here because we wrote TB in terms of TA. So now if we plug that back in, we can say that TB is equal to TA, which is W over 0.11 times sine of 60 over sine of 45. And if you multiply that, you get a value of 1.10 W. So this would be your final answer for TB. This was your final answer for TA. and TC was equal to W as we solved for. So that answers all three parts of the question. Okay, so our last problem is forces and projectile motion problem. This one is a little similar to the first one, as we will be dealing with projectile motion at the top of the ramp. But rather than being released from circular motion, this one is being pulled upwards, accelerated using a force. So you have a 3 kilogram box on a 30-degree ramp, and it is being pulled with a 45 Newton force. The ramp is 5 meters high, and once the box leaves the ramp, it is no longer being pulled by a force. It is just, it has some velocity that we will need to solve for, and it'll travel some distance horizontally, which is what we want to solve for. Okay, so I will set up the whiteboard and we can solve this problem. Okay, so we know that we have the ramp, 30 degrees, and a 3 kilogram box pulled upwards at 45 newtons. We also know that the ramp is 5 meters high. So given the fact that we're solving for projectile motion, it's safe to assume that we're going to want to know what velocity the box has at the top of the ramp. And if we're talking about velocity, we're talking about distance, and we're talking about, so we're talking about velocity and distance. So we know we're dealing with projectile motion here, but we know that it's a force pulling the block up the ramp. So knowing that it's a force, what would be a good first step to take here, Bhavdeep?
Well, knowing that this is a force and it's being pulled up a ramp, it seems like I believe we could use something similar to, or actually we could use Newton's laws and draw a free body diagram and proceed from there and see what we can get.
Exactly. So when you're dealing with forces, almost always a free body diagram is a good first step. So that will be the first one. So this is the line of the ramp. I know that weight always goes directly downwards. So that would be mg. My normal force is always perpendicular to the surface. And the problem did state that it was a frictionless ramp, so I do not need to worry about that. But I do know that there's a pulling force up the ramp, and that is force F. So are there any other forces acting on this object, Bhavdeep?
I think we're okay, Freya, but I believe we have a little bit of an anomaly here where if the mg is downwards, how do we figure out how we get the how do we use the angle here, basically?
So in this case, I'll actually erase that. In this case, we have mg is downwards. So if we would like mg to kind of match the rest of our plane, which is at this sort of angle where we have y and x, we need mg to be along the same plane. So what we're going to do is break it into its components. So the y component would be in this direction, the x component would be here, leaving us with 30 degrees at an angle here. So this will be our y, and this will be our x. So by breaking it into components, we make mg part of our slanted coordinate system that we're using. So then working from here, we can write out our Newton's law equations. So in the x direction, we have our pulling force. And we also have our x part of the weight. So that would be mg sine of 30. And this would be equal to ma. And as we know that it is accelerating up the ramp, I cannot cancel out that a. It does have some value of acceleration. And in the y direction, we have the normal force minus the y component of gravity, which is cosine of 30. And in this case, can I say that the acceleration is equal to 0?
I believe we can, since there's no motion in the y direction.
Exactly. It's not moving up and down off the ramp. It is just moving up the ramp. So these are our two Newton's law equations. And from our second equation here, we can conclude that the normal force is equal to mg cosine of 30. So if that information were to be useful, that is a conclusion we can make. But as far as us trying to figure out what the velocity is at the top of the ramp, our x direction equation is going to be a lot more useful as it provides us with more information about the problem. So looking at this problem here, which part of it do you think is the relevant part of the problem that we're trying to solve for?
Well, I believe since the only things that kind of coincide between kinematics and Newton's laws would be the acceleration, I believe we should use the first equation to solve for the acceleration, since we're also given other quantities.
Exactly, yeah. So when we're comparing between forces and kinematics, acceleration is a common factor, so that is what we're solving for. So I have a 45 Newton force minus 3 kilogram box times 9.80 meters per second squared, sine of 30 equals 3 kilograms times A. And Bhavdeep, do you want to explain why I didn't say negative 9.80 meters per second squared?
In this case, we're not really concerned with the motion, and the 9.8 is essentially just the acceleration due to gravity because the weight of the box. So that's why we can consider it positive.
Right, and also, as we've already considered our weight to be a downwards force, we've already accounted for the fact that it's negative with our negative sign in the equation. So if I include another negative, then I make it positive, which it shouldn't be. So as I've already accounted for the negative in the equation, I leave it as a positive when I plug in my value. So acceleration, when you solve for it here, would give you 10.1 meters per second squared. And that would be the acceleration of the box up the ramp. So, okay. So we have this. Now, we know that it's accelerating up the ramp, but do we know its velocity at the end of the ramp?
I believe we can either find it out. Yeah, we should be able to find out the velocity using the kinematics equation.
Exactly. So we can solve for velocity, but we don't currently know it. What we have is acceleration. So I will clear the whiteboard so we can work on that. So we have our ramp, which is 30 degrees and 5 meters high. And we know that acceleration is equal to 10.1 meters per second squared. We also know that V initial, as it starts from rest, is equal to 0 meters per second. So given the fact that we know A, we know V initial, we can solve for the distance, so the delta x, which would be that distance up the ramp. So delta x in this situation would be equal, if we use our trig rules, to 5 meters over the sine of 30 degrees. So that's our trig rules. Can we use our kinematic equations from here, and which kinematic equation do you think it would make sense to use?
So I believe we can definitely use the kinematic equation. The most sensible one would be V final squared equals minus V initial squared equals 2 times delta x.
Yes.
That.
Yeah. So we have this kinematic equation here would make sense because we want to solve for V final. We have V initial, we have acceleration, and we have delta x. So this doesn't leave us with any unknowns. So plugging that in, we get 0 meters per second squared as its 0 v initial plus 2 times our acceleration, which is 10.1 meters per second squared, times our delta x, which is our 5 meters over sine of 30. And plugging that into a calculator, we get that v equals square root of about 202 meters per second squared, meters squared per second squared, which gives us 14.213 meters per second. So at the very top of the ramp, when the object becomes a projectile, it has a velocity of 14.213 meters per second, and we know that this is at 30 degrees because we know the angle of the ramp. So now that we have this information and we know its height, we've kind of gotten back to a problem that's similar to the first one. So we know that we have a 5 meter high launch at 14.213 meters per second and 30 degrees. So given that we have this information, Bhavdeep, do you think that we can solve for the x distance?
Well, we can start solving. To solve for the x distance, we might need the time it takes to cover the entire thing. So I believe as we proceeded in the first problem, we should first find out the time it took.
Exactly. So it's the exact same steps as the first problem. We have our delta x, or delta y in this case, is equal to v initial t plus 1/2 at squared. So plugging in our values, we have negative 5 meters is equal to 14.213 meters per second times, and as it's the y direction, we're looking at the sine of 30 times t plus 1/2 times negative 9.80 meters per second squared times, t squared. So again, using the same steps as the first problem, we are going to plug this into our quadratic formula, rearrange and plug it into the quadratic formula. But for the sake of us having earlier done this, I will skip that step for right now, and we will say that t is equal to negative 0.518 seconds, or 1.969 seconds. And again, we cancel out the negative value, telling us that it is in the air for around a little under 2 seconds. So I'll clear the whiteboard and we'll finish up the problem. So again, we know that t is equal to 1.969 seconds, and that v initial is equal to 14.213 meters per second at 30 degrees. So we do the same thing as we did for the first step. We have our delta x, which is what we're solving for. We have v initial times t plus 1/2 at squared, except in the x direction there is 0 acceleration. So we know that it is just equal to 14.213 meters per second cosine of 30 this time, times time, which is 1.969 seconds. This gives us a distance of 24.24 meters, and that would be our final answer. So this problem was very similar to the first one in the fact that we were dealing with projectile motion, but as you notice, the way that you got to your values to start your projectile motion problem was different. So make sure that you're aware of how to kind of mix and match to the different topics to use them to your advantage. If you see a problem that's talking a lot about velocity or distance, chances are it's projectile motion. If you see something that involves forces, often you're going to need to do your free body diagrams and Newton's law equations, and other things would, so you look for keywords that'll define the topic. Were there any questions on how we got to this answer? Okay. Bhavdeep, did you have anything to add to kind of what we just went over? Any tips?
Just generally keep track of how the thing is moving, and make sure that all right, make sure that you draw pictures constantly, because that's pretty much how we solve it. I drew a lot of pictures, and that's definitely useful. The goal of this course at the end of the day is to give you the ability to solve complex big problems which involve multiple steps. So make sure you can do that, and if not, just attend the essay sessions.